All right, you guys, this is about the fifth time I've tried to record this lecture, so my enthusiasm for the subject is not as high as it was. Boy. So what I've ended up doing is trying to split this lecture into two, because before I was making something that was absolutely huge and not able to post it onto iTunes. So let's try now. So we're going to be talking about plate tectonics, but we kind of have to back up and start at the beginning. And the beginning, what you want to have is your Earth Slice of Pizza handout that is in that week 7 folder. Now, if you look at Earth Slice of Pizza, you guys, it's like a slice of pizza. It's not meant to be scary. It's about the layers of the Earth from your feet down. And if you remember, we learned that the Earth is layered according to density, with the densest material in the center and the less dense material out towards the surface. Now, on the left-hand side of Earth's Slice of Pizza, we have the 3 layers of the Earth as defined by their chemistry. Okay, and then on the right-hand side of Earth's Slice of Pizza, we have the 5 layers of the Earth as defined by their physical properties, how they behave physically. So are they solid, are they liquid, or are they what we call a semi-solid, or something that behaves plastically? Alrighty, so let's start on the left-hand side with the chemical layers of the Earth. So what we have, it kind of looks like a hard-boiled egg. Now, you guys, the good news is you don't have to give me any numbers. You don't have to tell me how many miles thick or kilometers thick the core, the mantle, and the crust are. You just have to kind of remember that the crust is really thin, the mantle is thick, and the core is thick. And if you think about a hard-boiled egg, the crust is sort of like the shell, the mantle is like the egg white, and the core is sort of like the egg yolk. All right, and the crust is really, really thin. If that was an egg analogy, the shell would be much, much thinner than a typical chicken egg shell. All right, so the crust, that's where we are. When you take a walk outside, you're walking on the Earth's crust. We'll kind of talk about some of those other bullets in there when we get to them, but the Earth's crust is made up of our silicate minerals that we talked about a lot this last section. And there's actually 2 different types of crust. There's continental crust and there's oceanic crust. Continents are made up of continental crust, and the sea floors are made up of oceanic crust. All right, continental crust is thicker. Again, you don't have to know numbers, you guys, just who's thicker, who's thinner, who's less dense, who's more dense type stuff. Continental crust is less dense. Think about it. You and I do not have gills, but our ancestors did. They crawled out onto the continents many hundreds of millions of years ago and didn't need gills. They developed lungs because we breathe air not through water. And, you know, where's the story going? It's going to the fact that, well, why do we crawl out and why isn't water covering us? It's because the continents are made up of less dense material and it floats higher. So it is above the surface of the ocean. Now, the oldest continental crust is much, much older than the oldest oceanic crust. In the center of the North American continent, we have rocks that are up to 4.3 billion years old. And you know that if you see if there was no auto shop for Earth's crust, okay, and we had like an old beater truck. If you had an old beater truck that was really, really old, you've probably been in a lot of fender benders. And the same thing with Earth's really old continental crust. It's been around, it floats because it's less dense, and it's just been in a lot of fender benders, and so it tends to be strongly deformed. All right, and our generic material that we're going to say composes the continental crust is granite. Now you might say, well, what about sandstone? Well, sandstone's made up of quartz grains, and the quartz grains probably came from weathered granite. It's all good for just kind of describing a general low density material, silica rich. All right, oceanic crust, that is made up of that igneous rock basalt that we talked about. It was black, fine grain, and it's black because it's rich in iron and magnesium. It's made up of mafic igneous minerals. And not only are they higher temperature, but they're higher density. So oceanic crust is thinner, okay, it is more dense, and it's relatively undeformed when it's in place. The seafloors, we're going to talk a little bit more about this, are kind of like conveyor belts. And as long as the seafloor material, the basalt, is on the conveyor belt, it's relatively undeformed. Sometimes basalt can get scraped off onto continents, and we have a nice chunk right near Old Town Auburn on Highway 80. Now, that's not part of the seafloor system. To drive to work, I do not need a submarine. That has been scraped off onto the continent, so it is deformed and it's old, but typically in place seafloor is on the conveyor belt in the ocean, or along the ocean floor, and it's undeformed. Now, the oldest seafloor in place is about 180 million years old, and that's up in the northwestern corner of the Pacific Ocean. Okay, and we already said that it was made of basalt. All right, next layer down, the egg white. It's called the mantle. And again, don't write these numbers down, you guys. It's thick. And we're going down because we're going into more dense material. Now, this is made up of mainly peridotite, or that ultramafic igneous rock that we were talking about. It's really, really rich in olivine, so it's about as dense as you can get and as iron and magnesium rich as you can get and still be a silicate. Now, parts of it are solid and parts of it are capable of flowing. It's going to behave like toothpaste when it's capable of flowing. You guys, think about toothpaste. It's not solid and it's not liquid. It's what we call a semi-solid, or it behaves plastically. Okay, so we'll split that up when we get over to the right-hand side of our slice of pizza. That really thick mantle is also layered according to density, with the least dense stuff up by the crust and the most dense stuff down by the core. And you know, we've never been to the mantle, but pieces of the mantle are, come up enclosed in basalt that erupts on the sea floor. So we actually have chunks of that peridotite, which is very olivine rich, from the mantle. All right, so we got our thin crust. Remember, we have two different types of crust, continental and oceanic. We have our thick mantle that is made up of mainly peridotite or ultramafic igneous rock. And now we're ready to talk about the core, and we're going to have a major chemistry change there. Okay, the core is made up of iron and nickel, and it is very, very dense. If you look at the average density of the core, it's more than twice the densest part of the mantle. So it's really pretty dense. And then you, again, don't memorize all the numbers. It's thick. And then that little statistic about, it's not very much of the volume of the Earth, but it's double that of the mass. It's kind of like, angel food cake is a very light cake, but then think about a really dense piece of cake that kind of makes you feel sick. It's so dense and heavy. That's sort of like the core. It's really dense and heavy, even though it's small. All right, and we have lots of evidence that we have an iron nickel core. We haven't been there, obviously, and luckily it doesn't come out to visit us because that would be pretty violent. But what happens is that, we have an Earth's magnetic field, which we'll talk about later, and we'll also talk about in our earthquake section what happens when earthquake waves pass through the Earth. It's pretty cool. All right, so you guys, we are ready to take those three layers chemically and now go over to the right-hand side and talk about the 5 physical layers of the Earth. And again, physical, you're like, well, what's that mean? We talked about physical state of matter, solid, liquid, gas. And first of all, there's no gas layer inside the Earth. So we're going to have solid and we're going to have liquid. But we're also going to have a layer that's semi-solid, or what we call plastic. It behaves plastically, your toothpaste layer. Okay, it's not really toothpaste. I get that sometimes. But it behaves like your toothpaste. It's not a solid. It's not a liquid. Now, the lithosphere is the outermost part, the outermost layer of the Earth's surface according to how it behaves physically, and it does include the crust. Now, the crust is relatively cool. It's pretty darn cool, and it's sitting on top of that warm mantle, and the top part of that warm mantle cooled and stuck to the bottom of the crust, and now it's behaving as the lithosphere, as a single rigid plate. So a little bit of that plastically flowing stuff is now cooled and stuck to the bottom. So its behavior is different. It's solid. It's rigid. Okay, everything we learned about continental crust and oceanic crust, now we'll just roll into continental lithosphere is thicker, it's less dense. Oceanic lithosphere is thinner, it's more dense, etc. So, what we learned before works here too. All right, the next layer down, we're carving up the mantle. Remember, the first part of the mantle is now stuck to the bottom of the crust, making up our lithosphere. Now, the next part of the mantle down is the asthenosphere, and asthenos means weak. And so this is the weak sphere, the part that is capable of flow, the toothpaste. Okay, so toothpaste flows. Okay, it doesn't just have to be liquid to flow. Toothpaste flows. You know that every time you squeeze your toothpaste tube. And this is what our rigid plates are going to be moving over. We would never have earthquakes if it wasn't for this toothpaste layer. Okay, it is, again, it's the mantle, so it's made up of the peridotite. Now let me show you that last button, or the last bullet there. Is actually easier to show you. Now you guys look at this picture, it's pretty cool. We've got the continental crust and the oceanic crust, and you can see the continental crust is thicker and the oceanic crust is thinner. Now that upper part of the mantle has cooled and stuck to the bottom of the crust. And, you know, whether it's oceanic or continental lithosphere is just determined by what type of crust is embedded in it. And, you know, all the rules stay the same. Now, where it's labeled lithosphere in the continent, you can see it goes down to that purple layer. When you get from the black to the purple within the lithosphere, there's a huge chemistry change, but they're solid, they're stuck together. Now, when you go from the purple, where it says lithosphere, down to the very first part of the asthenosphere, there's no chemistry change, but there's a physical change. We're going to go from solid to plastic or toothpaste-like texture. Okay, so there's not a chemistry change. They're exactly the same chemistry-wise. It's just a physical change, going from solid to something capable of flow. Okay. All right, now we've been carving up the mantle, and when I was young, it was okay to just call it what's left of the mantle, but, you know, no, somebody needs to call it something special. So mesosphere or middle sphere, this is what's left of the mantle, and it has gone back to solid. Now, you guys, before when we talked about metamorphic rocks, we talked about the deeper you go into the earth, the hotter it gets, and the deeper you go into the earth, the higher the pressure is. And what the pressure is, the deeper you go, is just the weight of the overlying rocks. And so the deeper you are, the heavier it gets. Now, pressure and temperature are not friends. They actually fight each other. And if temperature wins, things go to liquid. If pressure wins, things go to solid. And in this battle, pressure wins. And the mesosphere is back to solid. Okay. So once again, we've taken the crust and the mantle, and we've basically made 3 layers out of it. So we've got the lithosphere, which is the crust, plus the upper part of the mantle that's cooled and stuck to it. We've got the asthenosphere, that part that is capable of flow like toothpaste. And then we have the mesosphere, which is back to being solid and rigid and brittle. All right, here's a little hint for what's coming. We're going to actually have the 2 different layers of the core. It's still iron and nickel. It's everything we learned before. But, you know, that temperature and pressure battle goes on, and temperature is going to win. The outer liquid core, it's liquid. It's a very thick liquid. That's what viscous means. But it's liquid, and it does flow, because not only does it flow because of heat, but it also flows because the Earth is rotating. Now, this is what's going to create our magnetic field, and we will be talking about the magnetic field later on. All right, let's go down a little deeper, and pressure's going to win this one. It's back to solid. Yeah, it's really, really hot, and it's under a lot of pressure, but pressure just overcomes the heat, and it goes back to solid. Okay, so the solid inner core. All right, kind of going back in the first section, we talked a little bit about the external heat source of the Earth being the sun, and I think we mentioned the internal heat source, radioactive decay in the core. Now that's important. The radioactive decay in the core is what heats up the inside of the Earth, and there's about 5 billion years worth of that heat left. Now, when that heat stops, you know, in 5 billion years, we're not going to have any more mountain building, we're not going to have any earthquakes, anything like that. So I know it's still there. We're still having lots of active earthquakes. All right, convection currents. We talked about convection currents in the sun. We're going to talk later about convection currents in our atmosphere, but it's time to talk about convection currents in the asthenosphere. All right, there is a video in your folder about a lava lamp, and a lava lamp's a great example, but so is a pot of boiling water. You've got a heat source. You're heating up the water in that pot. When the water heats up, it expands. When it expands, it becomes less dense. When it becomes less dense, it rises up. Gets up to the surface away from the heat source, and it cools. When it cools, it condenses, and when it condenses, it becomes more dense, and it sinks down. And so this is a convection current. It happens in the sun, it happens in your pasta pot, it happens in a lava lamp, it happens inside the asthenosphere, and it's going to later on happen in our atmosphere. So this is really important. And don't just say hot, rise, cool, sink. It's hot, you know, it heats up, and it becomes less dense. That's why it rises. It cools down, and it becomes more dense, and that's why it sinks. Sorry, my dog's freaking out. Now, this looks like a scary word. It's not so bad. It's isostasy, and all it means is relative floating. I used to do a little demo, and I would have a piece of balsa wood. Balsa wood is very light, low-density wood. It's kind of like a cork, let's say. And then I would have a piece of cherry wood, and I'd have a bucket of water, and I'd throw the balsa wood or the cork into the bucket of water, and obviously it would bob pretty high because it's low density. Then I'd throw the cherry wood, and the cherry wood not sink, but it would float a lot lower because the cherry wood's a hardwood or a more dense wood. So that's kind of like the continental and the oceanic lithospheric crust. The oceanic crust being more dense, floats lower in that more dense mantle. And the continental crust, being less dense, floats higher. So this idea of relative floating. Now I like this slide because just about 15,000 years ago, the continent was covered, the North American continent was covered with quite a bit of ice. Like halfway down North America, it was about a mile of continental ice sheet. And what it did was it actually took the North American continent and made it, more heavy and more dense, and it sank down. And then after that last ice age ended and the ice melted, the North American plate popped back up, and in fact it's still popping up. So this idea of relative floating. Now you guys, make it easier for you. Think about your Italian salad dressing. You shake it, you use it like I did tonight, and I probably could go in the refrigerator right now and it's already separated out. And the least dense stuff is on the top, and then the next, lower density is underneath it, and so forth, until the stuff on the bottom is the most dense. So it's just, where do things get placed according to how they float, with least dense on top and most dense below. Alrighty, before we can talk about plate tectonics, we need to talk a little bit about how we came about with plate tectonics. And so we're actually going to have to back up to the early 1900s and talk about a German geophysicist named Alfred Wegener. Now there's a lot of information on this slide. What do you have to know? You have to know Wegener, and you have to know that his hypothesis was called continental drift. Now this hypothesis did get rejected, and we'll talk about it. We'll talk about the stuff that he put in there that was brilliant and the stuff he put in there that was stupid and why it got rejected. But, this guy, if he had been born 50 years later, he would be the father of plate tectonics. The problem is that nobody knew what the seafloor looked like. We knew it went down and got deep, but they thought it was like a bathtub, and it's absolutely not like a bathtub. Okay, Alfred Wegener was the first person to say, hey, the continents move. That's pretty preposterous back then. Continents are huge, and some people today even have trouble believing that they move. But they do move, and he gave some wonderful lines of evidence to support that. Okay. Now his problem was when they asked, how do they move? He gave something really, really lame. Okay. He also said that in the past we have had a supercontinent, and he named that supercontinent Pangaea, and Pangaea means all lands. Okay, Wegener also said that supercontinent Pangaea, where all the continents were together, broke apart about 200 million years ago, and he's right. He didn't have radiometric dating. He didn't have supercomputers. Barely could fly around towards the end of his life. It's pretty amazing. He came up with some really brilliant things. Now, he said the continents drifted to their present positions, and when asked, hey, how did they move? This is where he messes up. He says he kind of pictured the continents plowing through the sea floor, kind of like an icebreaker breaks through ice. It's going to get worse, you guys. That's just bad. That's not the ugly. All right, here's a digital copy of one of the figures that he had in his paper that he wrote in 1915. And, you look at it, it's not preposterous, you guys. It's almost perfect. And nowadays we have supercomputers. You can fly everywhere. We have geochemistry. We have radiometric dating. He didn't have any of that. And for him to be able to figure this out was pretty amazing. Now, this is going to happen again in the future. The plates are moving around. Eventually they will all end up, clogging up together. It has happened before Pangaea. There was another supercontinent. And so, it's just what happens. And, maybe in the next 500 million years it will happen. So not in our lifetime. All right, here are some of his pieces of evidence, and I do have slides on each and every one of these, and they're brilliant. Okay, now one thing important to understand is that he did not discover all of this, but he's the first person to put it all together as evidence that the continents move. Now, I love history, and I love to read historical papers and things, and I was reading something written by Benjamin Franklin back in 1770. And it said, as soon as we basically had decent maps, he just kind of mentioned that he had a map, and boy, didn't it look like South America and Africa fit together like a puzzle. Okay, he never said they did. He never said, oh, they probably did, and now it's, moved to where it was. He never even indicated the continents could ever move. So, but as soon as we had good maps, people were noticing this, that, look, South America and Africa really do. Now, we're going to talk about fossils that predated the dinosaurs, okay? We're going to talk about rock units that match across continents that are now separated by huge oceans. We're going to have some climatic data, both I'll tell you about the glacial evidence, and I'll also tell you about the tropical and equatorial evidence. Now, this last piece of data sometimes causes problems. All of the previous bullet points were all data that the continents were together. And this last piece is going to happen 100 million years later, and it's going to be evidence that by the time the mammals went crazy and speciated and populated the Earth, that the continents were far apart. So just be a little careful of that piece of evidence. All right, I really like this slide because it actually shows two pieces of evidence. The first evidence is the fit of continents. And when you cut South America and Africa out along their continental margin, and the continental margin is the part of the continent that's periodically either covered by water or not covered by water according to is sea level low or high. When you do that, look at them. They fit together like a puzzle piece. And the reason is they were once together. And we'll talk about what tore them apart. The other piece of evidence there are continuous rock units. Now, you guys, lava flows. Think about a lava flow. And remember that we can identify lava flows and say that they're from the exact same source. We can radiometrically date them. We can do a geochemical fingerprint that's as good as DNA, human DNA, testing type thing. And we can be sure beyond a reasonable doubt that, they are from the same source. Okay? Now, if you think about where the continents are now, the South Atlantic Ocean separates those two continents, and they're separated by thousands of miles. Okay, no lava flow would flow off of South America, flow across the Atlantic Ocean, and flow up onto Africa. It doesn't make sense. It only makes sense when you put them back together, and they match perfectly. Okay. All right, now here are those before dinosaur fossils. The dinosaurs lived during a geologic period called the Mesozoic, and so these are Paleozoic or earliest Mesozoic reptiles. And you guys, look at the one up in the upper right-hand corner. He is squatty, okay? And that means he just is not going to swim across oceans. And so when you look at the distribution of these fossils that are not ocean swimmers, look at their distribution. Antarctica, India, and Africa for the one on the top right. The one on the top left is Africa and South America, again, separated by thousands of miles of the South Atlantic Ocean. Now, you might look at the mesosaur and say, oh, he's an ocean swimmer. Well, he's a swimmer, but he's a near-shore swimmer. You don't find them out in the open ocean. Loch Ness Monster sort of relative. They like inland seas. They like near-shore marine. And you find them in the tip of South America and Africa. The only way to explain this distribution of fossils is that the continents were not only together, they were together for a long time because old, short, and squatty guys had to walk pretty far to walk between the continents and distribute. We also see this with a plant fossil that is not distributed by water. Look at the wide range. It's in each and every of those southern continents there. Okay, so what does this support? This supports the fact that continents had to be together because, UFOs didn't come in and, drop off these 300 million year old fossils. Sorry, you guys. The only way they got there is basically by walking. And the only way they could have walked is if the continents were together. All right, crumpled bumpers. Now, if you walked out in the parking lot and somebody had nailed your car, their car, you would not have any doubt. And when continents have fender benders, even when the fender bender has, gone away or when the other vehicle is taken off, you know it. And did you ever look at the East Coast of the United States and wonder why we have the Appalachian Mountains? They're an old fender bender. And their matching parts are in the Caledonians in Europe and then the Atlas Mountains in northwestern Africa, okay, Morocco area. And you know, they don't make sense unless you put them back together. In fact, when they did all crash, when the continents all came together back to form Pangea, the Appalachian Mountains were probably as tall as the Himalayas. They're, not so tall anymore because they've been being eroded for about 300 million years. Okay, so here's another slide. You can see the configuration today on the left and then the Pangean configuration on the right. And you can match back up the crumple bumper. Now, you guys, I see kind of those things on the news where people are kind of lame and they get in a crash and then they drive away, hit and run. Okay, and sometimes they have actually left, their license plate is stuck in the other car. Now, that's not very smart. And here's an example. Here's a fender bender, and the bumper of the car in front is stuck on the car behind. And so, the same thing happened. We have pieces of the Caledonian and Atlas Mountains stuck in the Appalachians and pieces of the Appalachian Mountains stuck in the Caledonian and Atlas Mountains. So lots and lots of evidence. We've been doing it for a lot longer than CSI. Okay? It's exciting stuff recreating this. All right, so the climatic evidence. Now, if you guys saw that movie, The Day After Tomorrow, we went back into an ice age. And I hate to tell you guys, it's not a cheesy movie. I mean, there's cheesy parts of it, but the science is pretty sound. The only thing I might argue with is it wouldn't happen that fast. It happened in weeks that we went into an ice age, but it could happen in like 5 years. So, it's not good news. But when you saw it, the ice sheet started to descend over the North American continent, and it got about halfway down the North American continent. And that's how it actually looked about, 12 to 15,000 years ago. So they didn't exaggerate it. But what you notice is that it did stop. Everybody kind of ran for Mexico and went, to more tropical, warmer regions, going towards the equator. Some people would say, snowball Earth, that the whole Earth was covered by ice, but if the whole Earth is covered by ice, we're not going to see any evidence of tropical and equatorial life. Okay, so let me just kind of explain this. So if you look in the bottom picture, we can tell when, ages of glacial events, and we can tell where they're coming from, what direction they're coming from. So if you look at that bottom one, we have a southern polar event, a glacial event. But look at the distribution. Not only does it go up to the equator, it crosses over the equator and goes into the other hemisphere. This does not make sense. Okay, but what makes sense is put the supercontinent back together and swing it over the southern pole. And it did have a glacial event. Okay, but look at that top picture. Look at North America. We're straddling the equator, and we have proof that there was life that was living in the equator in the tropics. If you guys go back east to Pennsylvania and West Virginia, we have huge coal deposits from that time. Those are the equivalent of tropical rainforests of those day and age. Okay, and there's also a lot of coral evidence that they find in the tropical and equatorial regions. You guys, coral does not grow in polar regions. My dog's freaking out because the cows are outside, just so you know. There was no such thing as a snowball Earth at this point in time. It makes sense when you put back the supercontinent, swing it over, and for the exact same time period, we have lots of coal being deposited in North America and in Eurasia, and we also have lots of coral evidence. All right, now this last piece of data, this is not from 300 million years ago. This is fossilized, mammals. And what happened was after the dinosaurs went extinct about 66 million years ago, the mammals went crazy. They filled all the open spaces left behind by the dinosaurs. And so we speciated, radiated, we went crazy. And what happened is that when the mammals, kind of went crazy, the continents had already started pulling apart, and in fact were very far apart. Think about it. If you want to see a kangaroo in its native place, you have to go to Australia. Australia is an island continent. And if you wanted to see giraffes and zebras to where they're native to, not the Sacramento Zoo, they're in Africa. Lemurs are only in Madagascar. In fact, South America had a very specialized group of life until the Central American land bridge went up about 5 I don't know, 5 million years. So these are the evidence that by the time these animals, they're not widely distributed. Okay, they're very specialized on their continents, unlike those short squatty things that could walk. These guys couldn't walk, and so they didn't walk, and we don't find their fossils. You don't find kangaroos in North America or Africa because they arose and evolved in Australia, and it was separated. All right, so great stuff. That is fabulous. Okay, here's the problem. Here's the bad and the ugly. So remember what I said about what he said. He said the continents plowed through the sea floor. And then somebody's like, well, you know, an icebreaker has an engine that's powered by fuel. What powers the continents? And this is the really lame thing. He said tidal forces. Now, you guys, we're going to talk about tides. I'm an oceanographer. I have a lot of respect for tidal forces, but believe me, they are not strong enough to pull a continent through the sea floor. If they were strong enough, they would stop the Earth from spinning and tear it apart. So I'm kind of glad they're not. And, you know, Wegener should have known better. He got backed into a corner, got desperate, and put his foot in his mouth, and his hypothesis was soundly rejected. American geologists were very cruel to him, and that's why I feel like we need to give him a little respect. Now, this gets rejected. Poor Wegener goes off, dies poor and, you know, with no friends and, you know, in shame. But 50 or 60 years later, we're going to bring the stuff back, and we're going to have to give Wegener his due because, you know, if he had just known a little bit about the seafloor, he would be the father of plate tectonics. All right, so plate tectonics. Let's fast forward to the late 1960s, the early 1970s. And why did it take so long? It took so long because, first of all, we had to learn all about the seafloor. Okay, and then secondly, we had to wait for all that data to be declassified. World War I, World War II, and the Cold War meant that we had to know pretty much everything there was to know about the sea floor because of the menace of the sea. U-boats, okay, German and Japanese submarines. And, you know, we had to know where could they hide, you know, where are they? And so the British Navy, the American Navy, we were pulling all sorts of equipment behind these ships to find out, you know, how deep is the water and what's it look like under the water in the ocean. And then they also pulled a magnetometer behind many of the ships to look for magnetic signals made by large metal objects like submarines. And that's going to actually be a shocker because it picked up the magnetic signal of the sea floor, and there's a pattern, and that's what will really kind of knock this out. Then remember, after World War II, we now are kind of have what we call the Cold War, where the Soviet Union was our enemy. And when I was a little kid, we used to have bomb drills. You know, we were sure the Soviets were going to nuke us, and then we were going to have to nuke them. And it was kind of sad growing up like that. And so they didn't want to declassify all that information because aren't you inviting, you know, the Russian subs to come camp off in the different good hiding places? So they wouldn't declassify it. Now, luckily, a few of the naval officers from World War II were geologists, and they went on to become professors at places like Princeton University. And they actually fought to have some of this data declassified and then interpret it, and we're going to get plate tectonics out of this. Now, if you type in to Google or something, who is the father of plate tectonics, up comes a name, Tuzo Wilson. He's not the father of plate tectonics, he's the office manager. He took the good stuff from Wegener, and then he took the good stuff from Harry Hess, the naval officer professor at Princeton, which I'm going to tell you, and this is going to be how the continents move, that missing mechanism, and he glued them together and he called it plate tectonics. Now, he was a fine scientist, I'm not knocking him, but this wasn't his thing. It should be, you know, who's the father of plate tectonics? Should be Harry Hess and Alfred Wegener. So plate tectonics, we're going to give you a different definition here in a little bit, but it's sort of like continental drift, those good things, plus this missing mechanism. It's called seafloor spreading. Okay, so this is going to be how continents open or continents move, and it's because oceans open and close. So we'll talk about that. And we're going to talk about, you know, first of all, plate tectonics became a theory really fast because many groups of scientists who are independently studying totally different things, paleomags, sediment ages, seafloor ages, hotspot tracks, earthquakes, they, you know, saw this hypothesis come out and said, aha, I'm going to look at my data and see if my data might make that hypothesis get rejected. And all of their data supported the hypothesis of plate tectonics, and so it became a theory fast. And it's still a fabulous theory, and it's the theory that, unifies all geologists. All right, Harry Hess, that Princeton professor, got a lot of respect for him. What he notices, you guys remember the bathtub model of your ocean? Absolutely not. Imagine your bathtub with a volcanic mountain range running right down the center. Ouch. That's exactly what we have. And then we have these deep ocean trenches. And, he made sense of all this pattern of what the seafloor looked like. And he figured out that new seafloor is being made at the mid-ocean ridge and seafloor is being destroyed at those trenches. And he called this seafloor spreading. And those convection currents we talked about earlier are what's powering it. A picture's worth 1,000 words. Let's look at this. All right, cross-section through a mid-ocean ridge. So see where the red is? That's the mid-ocean ridge right in the center where you can see kind of the darker oceanic lithosphere there. You can see it says the mantle. We're going to call it the asthenosphere. You can see the convection current. The convection current is coming up. It's rising. That material's rising underneath the mid-ocean ridge. Okay. Now, remember the conveyor belts. There's two conveyor belts moving away from that mid-ocean ridge. So new seafloor is made at a mid-ocean ridge. It moves off in both directions symmetrically and becomes progressively older. Now, it's cooling as it gets older and it's condensing. So look, it floats lower. Now, eventually, we are going to destroy that seafloor. And you can see we have the trenches labeled, and you guys know about trenches. You know about the Marianas Trench, the deepest place in the ocean, 36,000 feet deep or something like that. That is a subduction trench where seafloor has a head-on with something less dense. And on the right-hand side, it's a continent. Continent is less dense. So the seafloor gets shoved back under and eventually melted, and it gets recycled, and we call that subduction. So what Harry Hess said, new seafloor is made at the mid-ocean ridge, moves off, becomes progressively older, and is eventually subducted beneath, on the right-hand side, a continent. And it's driven by the convection cells in the asthenosphere. So this was the missing mechanism for how continents move. Now we'll look at this a little bit more. Continents move because oceans open and close. And you guys remember that North America and Europe and Africa were all together, and now they're not. It's because an ocean opened, and that opening ocean has actually moved the North American continent to the west while moving Eurasia and Africa to the east. And we'll look at that. It's pretty cool. All right, so new seafloor is being made at the mid-ocean ridge. There's high heat flow. Now let me back up, you guys. That's pretty important. Now, if you look in the asthenosphere, you'll see that's the plastic stuff where it says mantle and convection cell. But look where it says hot molten. That's liquid. Okay, we're going to talk about that specific type of melt that happens there. But if you put your hand right above that, and we can pretend like your hand was a very sensitive instrument, that's an area of what we call high heat flow. We can measure the heat there because it's much higher than if you move your hand over, a couple inches to the right or left. And that's because that asthenosphere, that hot area, is closest to the Earth's surface, right there. So a lot of times we can just nowadays with a satellite sense remotely and figure out where all of these things lie because they're going to lie in areas of high heat flow. All right, it moves off the mid-ocean ridge. MOR is mid-ocean ridge. Cools, becomes more dense. We talked about that. It does. The seafloor becomes deeper and deeper the farther from the mid-ocean ridge. Now, we know that the Earth is basically staying the same size. And so if we're making new seafloor, we've got to be destroying it somewhere. And where we're destroying it is those trenches. All right, it's denser. Seafloor is denser. That was really important. Oceanic crust, oceanic lithosphere is dense. And so it's going to be forced back under and go underneath the continental crust and lithosphere, and it's going to melt in the asthenosphere. Okay, now if you remember, I mentioned that the oldest in place continental rocks are 4.3 billion years old. That's incorrect. I'll have to fix that. 4.3 billion years old. And the oldest in-place seafloor is about 180 million years old. Okay. Now, it all has to do with density. The more dense seafloor is constantly being recycled or subducted. And the continent is so low density that it is, it's like pond scum. You can't get rid of it. It's so floaty or buoyant that it never gets shoved under. It never gets remelted like that. So it tends to stick around for a very, very long time. Okay, so it's all tied into the density. So remember, that's the oldest rocks we have found are actually in the North American Shield, so in the North American continent, and in the center, they're 4.3 billion years old. All right, so back to this, mid-ocean ridge. New seafloor made at a mid-ocean ridge, moves off, becomes progressively older, eventually comes in contact with something less dense, so it gets subducted and recycled. So, you know, your conveyor belt, it comes up and eventually your conveyor belt goes down. But your conveyor belt at the supermarket, it doesn't remelt and reform, but this is what would happen along the seafloor. All right, some of the other evidence that's going to support this is the age of the seafloor. Now orient yourself, find North America, South America. All those bright colors are actually the ocean basins. The red is new seafloor, and then if you kind of look, you got a stripy pattern. And the age of the seafloors totally supports that new seafloor is made at a mid-ocean ridge. Let's look at the Atlantic Ocean because it is relatively younger, so it is very symmetrical. Okay, the Pacific's not symmetrical, it's very old, and it's pretty cool. It's very complicated though. And if you look at the stripy patterns that you have in the Atlantic, what you'll notice is they are really symmetrical. If you've got one stripe on one side, you got the same thickness of a stripe on the other side. So it moves off in both directions, becomes progressively older. This is totally supporting plate tectonics. Okay, so what does the theory of plate tectonics state? It states that the surface of the Earth is made up of a number of rigid lithospheric plates, and they're moving. Okay, you guys, they're moving. You know that. Earthquakes. Okay, they interact at their edges, and we're going to find out there's 3 different ways they can interact. And at all of those boundaries, we're going to have earthquakes. Okay, and why are they moving? They're moving because the asthenosphere is capable of flow. Okay, it's that toothpastey stuff. If that was all solid, they wouldn't be moving. All right, here's some great stuff, some earthquake data. Now, we've been collecting earthquake data for thousands of years. If you doubt me, think about it. If you grew up in at church, you went to church school, we sang a little song about the walls of Jericho go tumbling down. And Jericho is a biblical city. And there is a Jericho, and it's built on the Dead Sea Fault. Okay, if you build a city along a big fault like that, it's going to fall down periodically, just like Los Angeles and San Francisco, which are built on the San Andreas Fault, do. And so we have lots and lots of earthquake data, and obviously it's gotten more high-tech in the last 50 or so years. But look at all this. If I just put up all the earthquake data, most earthquakes are happening on plate boundaries, those edges. And if you took a red pen and connected all those dots, you guys will have discovered the plate boundaries. Okay, you're probably looking at this going, oh my gosh, what do I have to know? You had better know you live on the North American plate. Okay, that's pretty important. And the other thing I want you to notice the North American plate includes the North American continent and part of the North Atlantic Ocean. Okay, the other thing you need to know is the Pacific Plate, because I grew up on the Pacific Plate. I lived 30 years on the Pacific Plate. San Diego, Los Angeles, Santa Barbara, parts of the Bay Area are on a totally different plate than the majority of the United States. So we're really going to kind of concentrate on those two plates, but there are, between, 8 and 20, kind of depends on if you're going to split it fine hairs or just kind of lump things together of these plates, and they are all moving. All right, there are 3 different types of plate boundaries. Now, you guys, there is a handout that is a table that is going to summarize all of this information, and so if you pull it out, you'll be in good shape. And we're going to talk about when plates pull apart, and we've sort of been talking about it. Mid-ocean ridges are divergent plate boundaries. Now, they're called constructive plate boundaries because we're creating new sea floor. So the 2 plates move apart, and then the basalt wells up to fill it in. Now, you guys, I was a biologist, got to give you a gross analogy. If you had an injury to you that split your skin, okay, blood and serum from below would come up and fill in that crack and make you a nice scar. And that's exactly what happens. When you split the surface or the skin of the earth, blood and serum from below, or basalt, comes up to fill it in. All right, mid-ocean ridge system, that underwater volcanic mountain range. If I gave you a pen and I showed you the map and showed you the mid-ocean ridge system, you could connect the dots. It really does go all the way around the Earth. It's pretty amazing. Okay, here is a close-up of the mid-Atlantic ridge in the Atlantic Ocean, that relatively young ocean that opened up and pulled apart North America, Africa, and Europe. And I want to talk, I know I have another slide coming up here about that melt, that where it says magma chamber, that is liquid, okay, and that's basalt. Now, as that toothpastey material in the asthenosphere rises up, it's rising up because it's less dense. Remember that temperature and pressure battle. As you move up towards the Earth's surface, the pressure becomes less and less. And so temperature is going to win that battle when it gets up closer to the surface, and it's going to melt. It's going to turn to liquid. And so you have these huge, long lines of this liquid underneath the mid-ocean ridge system. Okay, and here you can see the plates pulling apart, and we're seeing the edge of the North American plate and the beginning of the European plate there. All right, now when the supercontinent was together, how did the continents pull apart? They pulled apart by something called continental rifting. And, continental rifting, if it can continue on, it will open up an ocean. And that's exactly what happened. Now, we have continental rifting happening right now, and it's happening in Africa. And in fact, it's actually happening not too far from home, too. But we'll talk about the Great African Rift Valley. Now, when continents start pulling apart, we're going to have that basalt coming up. They always pull apart in a really weird pattern, and it's the Mercedes-Benz symbol. Look at the Mercedes-Benz symbol. It's 3 120-degree angles. Okay, and check this out. If you see the Red Sea, the Gulf of Aden, and then where it says the Afar lowlands, there's your Mercedes-Benz symbol. And this is an area, again, if my hand was that sensitive tool, it would have high heat flow, because this is where the continent has been thinned and stretched, and the asthenosphere is very close. In fact, there's a lot of basalt in that area where the Mercedes-Benz symbol is. The Red Sea and the Gulf of Aden have opened a little bit farther, and the Great African Rift Valley, that starts with the Afar lowlands and goes down to the different lakes down a little bit more south than that. It hasn't opened as fast or as far, but there still is high heat flow, so it is opening. And when I was little, my parents took me there, and I can attest that there's these deep valleys, there's a lot of basalt, there's cinder cones, there's a lot of standing water, lakes and things like that, because it's low-lying, and so that's where the water will go to. They get a lot of small earthquakes that are also shallow. When plates pull apart, you get shallow earthquakes. Okay, so we have that happening here. Now, the Gulf of Aden and the Red Sea are what we call linear sea stages. They've opened enough, the water comes in, the ocean comes in, and if that heat keeps happening, they will continue to open up an ocean. So, I mean, if you look at that earlier picture, Saudi Arabia used to be part of Africa, and it's actually rifting off Africa and barely attached. Okay, so let's look at this. You guys, this slide, the Great African Rift Valley is at B. The Gulf of Aden and the Red Sea is at C. And then D is if that continues on, we can get the Atlantic Ocean. Now, somewhere between A and B, we have a similar situation. It's not quite to B, and it's a little bit past A. Just to the east of us, we have the Basin and Range. It basically, from the Sierra Crest, you can stand and look to the east. It stretches from the eastern side of the Sierra all the way to Salt Lake City, and it's an area that's thinning and stretching. So, in a couple 100 million years, we could actually rift open an ocean there. So, kind of exciting. Now you guys can see that the continental crust thins, stretches, and eventually by the time we're at B, we have some basalt. Look at the difference. You can see the sea floor there. The ocean just hasn't come in yet. By C, the ocean has been able to come in and fill that in. And if that heat source continues, we will open up an ocean like D. And that's what happened with the Atlantic Ocean. And it continues to open. Okay, and it can actually stop at any of those stages. And there's great examples. There's a place in Death Valley that's a failed rift that stopped at the B stage. The energy stopped. It stopped, opening, and then it just filled in with sediments. Later on, we're going to talk about the continental margin. And if you guys notice the continental margin, think about the east coast of the United States. It's what's called a passive margin because the continental crust and the oceanic crust are glued together. There's no plate boundary. Okay, they are the same plate there. All right, now that decompression melting that I was talking about that happens right under the mid-ocean ridge, this is important that you understand it because we're going to talk about a different type of melt that is completely different. So decompression melting happens because as that magma rises up, or the asthenosphere of the material rises up, the overlying weight, the overlying pressure is reduced, and it will go to liquid because temperature will win as pressure decreases. So decompression melting happens underneath the mid-ocean ridge.